Hello, it's Yury Kashnitsky, Senior Machine Learning Scientist at Elsevier, Netherlands, and today we're going to discuss firing a cannon at sparrows or BERT versus logistic regression, an application to text classification which we'll be doing with HuggingFace and Catalyst, and whether we are going to deploy such a monster as shown in this picture, this BERT model. We'll start with a quick recap on BERT, then we'll be discussing NLP classification pipelines with Catalyst, and then an application to KPN chat classification. So KPN is a telecom operator in Netherlands that I've worked with. And we're going to discuss BERT language model fine-tuning to this specific domain, and then BERT classifier fine-tuning, with some afterthoughts whether it's worth training BERT or just logistic regression is good enough. So a quick recap on BERT. So first of all, it's indeed another revolution in deep learning. So I wouldn't say it's an exaggeration. So this time it's a revolution in NLP, or how Sebastian Ruder described it, NLP's ImageNet moment has arrived. So BERT has beaten, just smashed all other competitors on GLUE benchmarks in October 2018. And it's based on another seminal work introducing transformers. So attention is all you need. So this is a seminal paper, and BERT is a follow-up, and it stands for bidirectional encoder representation from transformers. So the first word is bidirectional. So let's take a look at the example. Why does it improve encoder representation, this bidirectionality? So we can take a look at a word bang, and we can see that it can mean different things depending on context. So in the first example, we went to the river bank. We see that the left-hand side context is about water, is about river, and then obviously bank means just the river bank. And then in the second phrase, I need to go to bank to make a deposit. Obviously bank is used in a completely different context, and we can actually infer that taking a look at the right-hand side. So to bank, to make a deposit. So we can see that indeed bidirectionality can help in this small example distinguish between different context of the word bank. A bit of technical details how BERT is processing text. So it introduces a couple of special tokens. So it starts with a CLS token. It's a classification token. And then the final token is a special separator token. And BERT uses word piece tokens, so meaning that it works on subword level. So a bit more extended example, BERT can actually process two sentences, so we'll see examples in different applications. So we can start with a CLS token. So this first one is CLS token. Then we can have the first sentence, then a separator token. Then we see that we applied word piece, so which splits the word playing in this example in two subwords, so play and this ing, so a subword, and then it all ends with a separator token. For all these tokens, BERT learns embeddings. So these yellow ones are token embeddings. And then to distinguish first sentence from the second one, BERT learns segment embeddings, which are just a separate embedding for the first sentence and a separate embedding for the second sentence. And then BERT relies on attention mechanism, or self-attention, which is actually order agnostic. So if we just shuffle all tokens, it will work the same. And so to restore some information about positions, BERT either learns or uses a special formula for position embeddings. I'm not going into details. We'll be interested in this processing just to understand what applications BERT can support. So first of all, subtasks that BERT is trained with. So the first one is masked language modeling. So we are masking 15% of tokens, and then 80% of them are replaced with a special mask token. And then the idea is then to predict the word that we replaced with a mask token. And then a bit more details. Yeah, some 10% of them are replaced with a random token, but I will just deliver the main idea here. So we are not diving into all the details. So for now, let BERT be a black box. In this case, it's just a yellow rectangle. And an input can be masked text. So the original sentence was, the poor don't have any money. And then we'll be replacing some words with a mask token. So we start with the, then the special mask token, don't have any, and then again mask token. So we replaced poor and money with this special mask token. And then the model needs to understand, to reconstruct these original words, poor and money, that we replaced with this mask token. Another task is next sentence prediction. So for two consecutive sentences, we would like to predict whether they are, whether one is it follows from the former. So whether the latter sentence follows the former. So for instance, Amsterdam is the capital of Netherlands, and many millions of tourists visit it every year. So these two sentences naturally follow one from each other, and so that will be this target is next. So one is next compared to another. And if two sentences are not related at all, that will be class 0, and basically that's a binary classifier. Small spoiler, actually, this masked language modeling task is enough, and this next sentence prediction task didn't add actually a lot. And so in the follow-up experiments with larger Roberto models, they actually got rid of next sentence prediction task and only used masked language modeling task. Now we can discuss fine-tuning and applications. So we are still treating this BERT as just a large black box. But let's take a look at applications. So first family of applications is sequence classification. So we have a single sentence. This is just a sequence of tokens. The number 0 is CLS token, and these yellow rectangles are embeddings learned for these tokens. And then it passes through all these large model. And then finally we have also, these green rectangles will be the output of the model, and the first one will be the output for the CLS token, and we basically just learn a simple dense layer here to perform classification. It can be either binary classification or multi-class or multi-label, so these all fall into the same family, and we'll take a look at some applications of this class. So examples are pretty simple. So it can be any sequence classification, so basic text classification, classifying news into different categories, or sentiment analysis, or any other text classification. Then another application is sentence pair classification. So here we have two sentences separated with a SEP, with a special SEP token, and we predict the same. So we predict some label or a set of labels for a pair of sentences. And here a classic example will be natural language inference. So whether one sentence is a follow-up for another one, so how it relates to the first sentence, whether it's an entailment or inference or things like that. An extension of this example would be question answering. So again, here we have a couple of sentences in the input, but the first one is a question, and the second one might be a paragraph. And then now the output is a bit more interesting. So we have these green rectangles stay for the transformed output, but now we can learn something more involved. So let's suppose that here, so we've got a question, and here in paragraph we can have an answer to this question, and we can actually learn positions of. So we can learn the start position and end position of the answer, and so basically for each token representation here close to the output of the model, we'll be learning basically some probabilities that it's a start of the answer span or an end of the answer span. So here is a small example. question answering with Google natural questions. So it's a pretty large data set, and it's comprised of real questions to Google search engine. So one of the examples is, where's the world's largest ice sheet located today? And here in these competitions, we were provided with a Wikipedia article, and somewhere in this article, probably there is an answer to these questions. And the model can learn these start and end positions, and we can find. So the model can highlight a paragraph where a long answer is contained, and then even more specifically, we can find the actual answer that's at Antarctica in this case. And it's basically all done with this scheme. So we provide a question, we provide a paragraph, so in this case from Wikipedia, and we can learn actually. So we got the training set, yep. So we got this labeling for the answer positions, and we can provide these start and end token, and then the model needs to learn these probabilities that each token is actually start or end of this answer span. And then sequence tagging is, again, we have a single sentence as an input, and then it's processed through all these large BERT model, and then we have labels for each token. And examples include named entity recognition, or maybe reference resolution. So we are making a prediction for every token. So in this example, yeah, we're predicting whether some token is a person or an object. It can be a location. So this example is for named entity recognition. For coreference resolution, will be for each token will be predicting whether there is a whether there is a coreference. So for instance, I entered the room and saw Julia. She was talking to Laura, smiling and laughing. So we can have a word she, and then we'll be predicting. So for each token, we'll be predicting a probability that it actually refers to she. So something like that. Okay, so that was a very quick recap. So we didn't dive into how BERT actually works. There is a ton of materials on that. I would recommend some of them. So I would recommend videos by Chris McCormick. So it's a pretty simple introduction to BERT. And then, of course, all the great blog posts by Jay Alamar, the illustrated transformer, visualizing a neural machine translation model. So actually, Chris McCormick relies on Jay Alamar's posts and extends them. I've also got some slides on RNNs, attention transformers, and BERT. And now let's move on. Moving to Catalyst. So Catalyst is a framework for reproducible deep learning experiments, and it combines the best from two worlds, from the world of academia and researchers in deep learning, and practitioners and developers. So it's a nice bridge between this world of researchers who typically have cool ideas but typically write pretty bad code, and developers who are better at actually writing reproducible pipelines, but then they are not so keen in deep learning. So from a researcher perspective, Catalyst implements PyTorch best practices, all the different state-of-the-art models and optimizers, different schedulers, and it has applications to reinforcement learning, computer vision, and NLP. Yeah, actually contributed to NLP pipelines in Catalyst. So it started with reinforcement learning and computer vision, and I was the first to introduce some NLP pipelines. Not only me, but in a small team, we introduced NLP pipelines into Catalyst. And from a practitioner perspective, Catalyst provides reproducibility of experiments, and then these pipelines that you build can be easily reusable, and it provides some simple configuration, and you can easily implement distributed training and all the hacks like mixed precision training, and you can monitor your training. So all of that is turned on just out of the box pretty simply. Yeah, one of the features to mention is also saving checkpoints, so that you can always refer to your best checkpoint and then quickly pick it up and reuse later. So here I present text classification pipeline with Catalyst and DistilBERT. So this is for NLP, for text classification. Here in this presentation I'll highlight only some key parts, but I can easily refer to the Jupyter notebook. So Catalyst offers easy to use Jupyter API. So basically, Jupyter notebooks, and in this case it's a Kaggle kernel that you can refer to. And Catalyst also offers a bit more sustainable API. It's a config API. It has some better design. Maybe it's a bit more involved, so it's a bit harder to dive into that. But then when you get used to it, it's just like, Jupyter notebooks and then Python scripts. So it's more disciplined approach to developing pipelines. But I'll highlight the key parts from the Jupyter notebook, from that pipeline. So I'll just show how it's easy to use Catalyst in your NLP pipelines. So we always start, of course, with reading and processing data. So in this case, it's an example with Amazon pet product reviews. So just merely with pandas, we we read training, validation, and test sets from CSV files, and we've got a simple task. We've got a piece of text which is a review, and then we predict one of the labels. In this case, it's cats, dogs, and some more, some birds and some rabbits. Yeah, in this case, these are all dogs. So we just start with pandas, reading data. Then goes pure PyTorch. So we define a data set. So in this case, it's a text classification data set. We, as an input, we take these texts, which is just a list of our reviews, and then labels. And we define the model. In this case, we are using DistilBERT based uncased. Maximal sequence length that BERT models can support is 512 for these simple versions. Basically, text classification dataset just tells us what processing we need to perform and how we actually access an element by index. So we'll be accessing elements of these classification datasets, and that would return processed text and labels. So all of them are PyTorch tensors. And we initiate a training dataset and then a validation dataset. So just passing this text from the training set, and then labels from the training set. We'll learn this label mapping. And then, max sequence length, a hyperparameter, and then the model name for text processing. One final step with PyTorch data processing, we'll define a dictionary with two data loaders. Training data loader and then the validation data loader. So it will take batch size as a hyperparameter, and then it will take care of all the shuffling and then batchifying your input. So you see we defined a train dataset and a validation dataset, and then a simple wrapper would be these data loaders. So far it's just PyTorch, and we also define the model. So in this case it's DistilBERT for sequence classification. I tweaked it a bit in the kernel, but basically you can just import this implementation from HuggingFace transformers. And then typically in a pure PyTorch pipelines, you would have a training loop with maybe 200 lines of code. And with Catalyst, you can substitute it with a simple call to one method train. So we define a special object supervised runner. And we provide just one field to say that we'll be using features in this processed text, and then one additional field, attention mask. And then when we define the runner, we just pass all the models, criterions, everything that we defined earlier, all the basic PyTorch ingredients. We just pass these to to the train method. So we pass the model, we pass the criterion, so it's binary cross entropy loss, which we'll be using in a classification task. Earlier we defined optimizer and scheduler. So here go all the basic PyTorch ingredients, then data loaders, which we defined earlier, and then Catalyst supports a rich family of callbacks, so they offer a lot of functionalities. So we'll be keeping track of accuracy callback, and in this case we are also using gradient accumulation. So it's a small hack which can speed up your training. So when you are doing a backpropagation step, so in a simple implementation, you'll be doing parameter updates after each backward step, but you actually don't need to do that many weight updates. You can actually do several 4, 8, or 16 backward steps, accumulate all this information, and then do weights updates only once. So it's it's a well-known hack in training deep learning models, and Catalyst implements that as simple as just passing one callback. It can also support FP16 training with NVIDIA Apex. But actually pure PyTorch also supports it now, so maybe we need to compare here. And then we can also specify a directory to store logs. So all the checkpoints, all the TensorBoard logs will be saved here. And now finally inference. So just by the same token we define test loader here, so a test dataset and a test loader, so exactly how we defined train and validation loaders. And then we also have this second method, infer. So for the very same runner, we've got the infer model, which takes the very same model, the test loaders, and then with a special checkpoint callback, we can pick up the best checkpoint. So remember, we specified the log directory, and all the checkpoints are saved there, and then we can automatically pick up the best checkpoint according to validation loss. And finally, we grab predictions. I'm saying meh here, because it's not obvious. So from how do we actually get predicted probabilities for the test set? This might look awkward. It's sometimes we abandon using frameworks just because of one single line that we don't understand, one simple thing that's not obvious for us. Sometimes we have to struggle, but when you overcome such friction, then you'll see that it's actually in general it's very easy to use. Only maybe for some simple things maybe you just struggle a bit. Now let's turn to an application. So it's a task at telecom operator. It's chat classification. So it would be a very chrysematic, very simple task. The only difference is that it's in Dutch, and it's we have major categories. So first level categories and then second level categories. The task itself is customers talking to agents at a telecom operator, and they report all the different things, all the problems, all the problems with billing, technical problems, and so on. And basically, we would like to classify these into different groups. So these first level classes are very general. So it's billing or contract end. Or just service where we just need to help customer, logging in. But then we also have more structure, so all first level ones, classes like billing can be further elaborated. So peculiarities of the task are that all the chats are in Dutch, and then labeling is very, very expensive. So we don't have a lot of labeled data, so only about 10,000 examples, but we also have more than 1 million unlabeled chats. We had analysts actually sitting and working on labeling all these chats. So just understanding the content, understanding all these differences, whether the customer has problems with just receiving some receipt or the receipt was wrong. So all these different peculiarities, it might be in general class billing, but then all these second level categories might be different. So analysts spend a lot of time actually diving into all these details. That's why labeling was very expensive, and due to all the confidential GDPR issues, that we were not able to outsource that. So KPN staff was working on this labeling. Okay, so we are actually interested in achieving good results with as few labeled examples as possible. And one more peculiarity of this task, as mentioned, is structured classes. So we have hierarchical classes, with level 1 and level 2. But in this example, just for simplicity, we'll be considering only level 1. And the distribution is here, so the majority is a general class service, so it's all these basic issues that you encounter just using telecom operator services. Problems with logging in, where is information found, so all the small consulting on services. Then goes billing, then something like orientation and sales. A very interesting class is contract end, where people just mention explicitly in the chat that they are pissed off, and they would like to just churn. It's actually it's a very interesting task. So it's by definition it's data mining. So you've got all these huge millions of chats, and you would like to find meaningful insights there, meaningful information. So classification is just the first step to help analysts actually understand all of these and find insights in data. Also showing distribution of chat length in words. It's important, a big limitation of transformers is that they don't support very long texts. There is some progress here, so with lean formers and long formers, but it's for now it's more like in research phase. But with basic BERT model use, you typically work with short texts up to 512 tokens. And that's why it's important to analyze the distribution of your input length. So in this case, we see that some chats are pretty long, up to 2,500 maybe tokens, but the majority are shorter than than 700. There's some strange small peak here, but basically it's fine just to use it as is. So the model will cut these chats at 512 tokens, and it doesn't look like a big problem here. And then we will discuss two steps, language model fine-tuning and then classifier fine-tuning. So first of all, it's Dutch, and it's also a specific context. So these natural chats between humans, it's a bit different than Wikipedia. And then actually it means that in all cases when your domain is a bit different than Wikipedia or Reddit that maybe the model was pre-trained with. So when your domain is a bit different, it makes sense to fine-tune your language model. I did that with HuggingFace. If you just go to HuggingFace examples, there is a script run language modeling. I also referred to some helpful issues. Of course, it didn't work just out of the box. I encountered some issues, and I referred to one of the important ones. So this step is typically pretty expensive. So I used a single GPU, and training took a couple of days. And the final perplexity looks good. And also showing the loss. So it's important to keep track of things like that. Loss and the learning rate. Basically, I just used the HuggingFace script, and without a lot of details, I'm just mentioning that this step is important, and it actually helps a lot to fine tune to the domain. In this case, it's telecom operator data and Dutch language. And then the second step is BERT classifier fine tuning. That's what we did with the Catalyst pipeline that I shared. Here I'm showing learning curves. So first of all, we have these level 1, so these general 5 classes. And here in green, I'm showing BERT. It's actually a Dutch BERT, yeah, this BERT-che, it's just Dutch BERT. And what I'm showing here, it's on the x-axis, it's a dataset size. On the y-axis, I'm measuring f1 micro. In a multi-class setting, it's just accuracy. And I measured all of these with respect to a single validation, or we can say holdout set. I was actually interested in how quickly do we reach nice accuracy with a varied dataset size. Yeah, and we can see that BERT, it outperforms a bit the logistic regression. Yeah, and here I need to mention that it's logistic regression with tf-idf representation. So it's a golden rule in NLP, just use this model first, logistic regression and tf-idf. So we can see that, with about 4,000 examples, we reach some 80%, maybe 82% with BERT, but logistic regression is actually catching up. It's something like 76 F1 score. For level 2, where we have 50 classes, results are much worse. And in this case, the first idea is just to merge some of these level 2 classes. So it's to simplify your task. So when this was done, so it involved working with subject matter experts. So the number of these level 2 classes was reduced to 17. So we can take a look at which classes the model confuses, and then with a subject matter expert, we can just merge 2 classes, and that's a nice simplification. So in this graph, it's basically the same. The level 1 didn't change a lot. Only for level 2 we have a simplification, and the results here are actually much better, of course. But conclusions from these experiments are that we eventually have actually the same score for logistic regression and this BERT model. So that might be really depressing, demotivating, right? So we spend so much time with language model fine-tuning, then with classifier fine-tuning, and then eventually accuracy or F1 scores are just the same as for BERT and for logistic regression. So that's actually disappointing. But another conclusion is that pre-trained BERT model actually reaches decent scores much faster. So that's why I was building learning curves to explore this dependency. And what we can see is that BERT actually reaches some decent scores, some 77%, with only 500 examples. And as we can see, logistic regression reaches the same score with only with as much as 2,500 examples. So it needs 5 times more data to reach the same scores. So in case of really expensive labeling, this might be a very good argument to have a pre-trained model. So we started with describing data. We said that we have a lot of unlabeled data, a lot of raw chats, and labeling is expensive, so labeled data is scarce. So it's an ideal scenario for transfer learning. And indeed, we see that to some extent it works. So BERT achieves indeed good scores much faster with much smaller labeled dataset sizes. And the conclusion is that here we could have just used logistic regression. But if labeling is really expensive or we are in a scarce data world, then for sure transfer learning can help. But we don't forget about interpretability. So for logistic regression, we have a very nice interpretation, so we can just plot all the coefficients for all of the 5 classes. And I also introduced a class not classifiable, and we can just go through. In this case, it's Dutch, but you can see that for billing we have all these words: factuur, facturen, euro. So you even don't need to know Dutch to see that it's easy to interpret this model. And we lose these when we switch to transformers and this complex BERT model. So some afterthoughts that for simple problems like text classification, tf-idf and logistic regression is typically good enough. And you can struggle with all these transformers, with BERTs, and other heavy models without really good improvement. So in a simple text classification task, yeah, if just bag of words works well, if just lexics is already enough to do decent classification, then yeah, probably you just stay with tf-idf and logistic regression. And this contribution of a huge model, yeah, that will be just very small if bag of words already works well enough. Well, for some harder problems like named entity recognition or question answering, it makes sense to apply BERT for sure. Yeah, with question answering, you probably just struggle with even with the design, how you would use logistic regression and tf-idf in such scenario. Yeah, for sure, for harder problems, yeah, practical experience shows that yeah, it makes sense to use transformers. But as a side note, yeah, deploying transformer to production is a completely different story. So it's of course much harder than deploying a logistic regression model. And interpretability is also an issue. We have some interpretability with a linear model. And with BERTs, it's only being explored, so you can plot these attention masks, but it's yeah, sort of vague for now. It's only yeah, under research. And well, my personal conclusion is that transformers are nice to read about. They're cool to be applied on in Kaggle competitions, but they're pretty hard to work with. Thanks, cheers. Yeah, my nick in Open Data Science Slack is Yorko. So yeah, you're welcome with questions. Good luck.